All right, today we're putting on our detective hats. We've got a case to crack called the contiguous zeros problem. Our mission, should we choose to accept it, is to find a hidden boundary inside a list of numbers. But the real trick, we've got to do it as efficiently as possible. Let's get into it.
So, let me ask you something. If you needed to find a word in a dictionary, say algorithm, would you really start at the very first page and read every single word until you found it? Of course not. That'd be crazy. You'd instinctively open it somewhere in the middle, see what letter you landed on, and then decide to jump forward or backward. Keep that idea in your back pocket. It's the key to solving this whole case.
Okay, let's open the case file. Like with that dictionary, knowing what we're looking for is the easy part. It's how you find it that separates the rookie from the master detective. And our case today is all about finding the smartest how. Here are the facts of the case. We're given a list of numbers, what programmers call an array. The one thing we know for sure is that this list starts with a solid block of zeros. They're all together. And right after that last zero, it's just a mix of other numbers. Our job is to pinpoint the exact count of those starting zeros.
So, for example, take a look at this array right here. You can see it clear as day, 5 zeros right at the top, and then bam, the number 3. That little space right between the last 0 and the 3, that's the boundary. That's our crime scene. The count of zeros is 5, so our answer has to be 5. Seems pretty straightforward, right? Now, every detective starts with the obvious, plodding approach. Knocking on every door, asking the same questions. We'll call this the brute force method. It works, sure, but it's not going to win any awards for style. This method is exactly what it sounds like. You go to the start of the list, you check the first number. Is it a 0? Yep. Okay, that's 1. Move to the next spot. Is that a 0? Yep, that's 2. You just keep shuffling down the line, one by one, until you finally hit a number that isn't a 0.
Look, checking one by one is fine if the list is short, but what if our array had 1,000,000 zeros at the start? Or 1,000,000,000? We'd be counting all day. There has to be a shortcut, some crucial piece of evidence that lets us solve this thing way faster. So what is that key clue we're missing?
And this is where the real detective work kicks in. The game-changing clue isn't in any of the numbers themselves. Nope, it's hidden in the structure of the problem. And once you see it, you can be so much smarter about your search.
Here's the smoking gun. All the zeros are contiguous. That's just a fancy word for all grouped together at the start. This means if we check a number anywhere in that block and it's a 0, we automatically know that everything to its left must also be a 0. That single fact means we can stop checking one by one and start making those intelligent jumps, just like with the dictionary. All right, let's put this new clue into action with our first interrogation of the data. Instead of starting from the top, we're going to jump right into the middle and see what we find. This is step 1 of a powerful strategy to shrink our search space fast.
Let's set the scene. Our array has 10 spots, indexed 0 through 9. Let's think of a 0 as a yes and any other number as a no. Our initial search area is the whole thing. We'll put a marker called low at the start, index 0, and a marker called high at the very end, index 9. Our goal? To find the very first no.
So here's our interrogation plan. First, we find the exact middle of our search area. We're not starting at the beginning. Then we'll check that midpoint. For now, let's assume we find a yes, a 0. That tells us a lot, and we can immediately update our search area by moving our low marker. Finally, we'll do a quick calculation to see just how much of the problem we've already eliminated.
Okay, let's run the numbers. To find the midpoint, the formula is low, which is 0 plus high minus low. That's 9 minus 0, so 9. Divide that by 2, you get 4.5. But with computer indices, we just drop the decimal. So our first point of interrogation is index 4.
Now we go to index 4 and check it. Let's assume it's a yes, a 0. Because we know they're all contiguous, we can now totally ignore everything from index 0 all the way through index 4. They're cleared. So our new search area, our new low, starts at the very next spot, index 5.
So what's left to investigate? Well, our search now runs from our new low of 5 all the way to our high of 9. A quick bit of math. 9 minus 5 is 4, plus 1. That leaves us with only 5 suspects left. We started with 10 possibilities, and in one move, we're already down to 5.
So, what did all that work get us? This is the best part. This is the payoff. This is where our clever detective work really shines.
Let's see what that one single interrogation actually accomplished.
And this just lays it all out, doesn't it? We started with a search space of 10 different elements, 10 possible spots for that boundary. But with one single strategic check in the middle, we literally eliminated half of the array from our investigation. Poof, gone. Instead of 10 suspects, we have 5. This is so much more efficient.
So what do we do next? You guessed it. We do the exact same thing again, but this time on our new, smaller search space. This technique of repeatedly slicing the problem in half is a classic detective move in computer science. It's called a binary search. We just keep repeating the process, narrowing it down until we've cornered our answer. The case is almost closed.